Okay, archaeologists are in a data-intensive program. Knowledge acquisition is a dynamic process. There's an interplay between data, theory and practice, which is all somewhat mediated by the individual themselves. When they interpret or synthesize results, it's predicated upon their experience, their mood, their philosophical position, the weather, the recording systems they're using, the standards, and all of these vary. So there's an interesting interplay between all of the components involved in archaeology, but it's primarily a data and theory-led process. And to summarise this, we perform a whole variety of different experiments or excavations or data collection processes that provide us with evidence. And we perform more of these experiments and it gives us more evidence. We can connect the dots between this evidence and come up with a theory to explain what happened in the past. But a variety of different competing theories can be used to explain the same evidence. And as we gather more bits of data, we can eliminate the demonstrably incorrect theories. From the theories that remain, all of those theories make assumptions, but those with the fewest assumptions are more likely to be true. So we tend to focus on the theory with the fewest assumptions. That gives us an accurate picture of the past as we can. It may not be completely accurate, but it's closer than competing explanations. Now this kind of works for a primarily science-focused discipline. However, archaeology is a combination of science and arts, and multiple theories and multiple approach and multiple contextual viewpoints can be used to interpret the same data in an equally valid way. Our data comes from a variety of sources. From excavations, we have contexts, artifacts, ecofacts, soils, sections, plans. We move up scales into landscape analyses and a whole variety of other scientific techniques of lipid analysis, resistivity, geophysics, magnetometry. We collect all of this data. We have our primary data, and we have synthetic data, interpretation, site reports, academic reports, information that goes in sites and monuments records, and these tend to be decoupled, but they also tend to be siloed. We put them into heritage resources. Now, not all of these resources are accessible, and walls are built around them. And we come here against a battle between formal and informal groups because people naturally want to share, and people pass around data on USB sticks, for example. It's not necessarily the most effective way to get information from A to B. And it's created what English Heritage referred to in 1995 as the little used and inaccessible data mountain. So all of the new data that's added into the corpus has very little impact on the state of the landscape. This is not ideal. This percolates through down to decision making and policy, because we can only make decisions with the data or knowledge which is available to us. So that's the accessible knowledge, the things that we're aware of. There's also a whole heap of inaccessible knowledge that we're aware of as well. Stuff that's behind firewalls, stuff that's behind paywalls, stuff that's in paper format when we work in a digital medium, stuff that's held in a place that you just physically cannot get to. And so these barriers to access mean that we aren't working on the most up-to-date information. And there's a whole heap of other stuff that we're not aware of. So it gets into this Rumsfeldian process of the known knowns, the unknown knowns, and the unknown unknowns. And it's within this context that DART was commissioned. So DART is essentially a project looking at the dynamics of seeing beneath the soil and archaeological prospection. So in the past, for example, a ditch is dug, over time it's abandoned and fills up, again it starts to stabilise, and it's incorporated into part of the landscape. And people who undertake archaeological prospection tend to look for these residues or remains, and it can be through changes in soil directly, changes in topography, changes in crop, changes in moisture content, changes in chemical content. And the whole point of DART was to look at how we can improve this, how we can get a better baseline understanding of the techniques and approaches, and how these change over time, because the contrasts do change over time. The nature of the definition between two features varies as weather changes, varies as crops grow. And this has a particularly important factor, or is particularly important for different perspection techniques, particularly the more expensive ones like hyperspectral imaging. Now we set up a number of monitoring sites in the dry and wet part of England, between Diddington and Cambridgeshire and Harnhill in Cirencester. Within each of those areas we had well-draining fields well-draining soils and clay soils. On top of those we had our 4 monitoring sites, so we had our ditch feature. Within that we excavated a hole, which I'll talk about more in a moment. We ran geophysical surveys, and we took spectroradiometry readings looking at both the soil and plant growth. So our geotechnical monitoring, we dug our holes, we inserted a load of probes, so that's soil moisture and temperature. We took a load of samples, which we then analysed in the laboratory. Each individual area had its own weather station, so we could look at solar illumination, rainfall, and a whole variety of other derived characteristics. So we had this longitudinal data set of changes in ambient local conditions, particularly soil moisture down profiles, and the associated soil geotechnical information. Over a 14-month period, 16-month period at some of the sites, we collected a variety of geophysical techniques, geophysical measurements on approximately a monthly basis, so we could again look at how these contrasts change over time. Similar surveys were undertaken for crop monitoring using spectroradiometry, which is basically a ground-based hyperspectral analysis. It's where we derive these curves from, and so we could look at the changes of crop stress and crop vigor and crop growth parameters over time, and compare this to both hyperspectral and LiDAR airborne topography. It's not airborne topography, but anyway, I'll work on that. And other aerial photographs that are collected over, again, a multi-temporal basis. And the aim was it just to get a better understanding of what's going on within the soils and how that impacts on detection, but also to try and feed this through to decision-making processes, and to open up the data and the workflows so that it could be reused by a whole range of different stakeholders, which is really the focus of this presentation. So DART had 25 heritage, industry and academic partners, and we decided the best way to keep everyone informed was to adopt an open science philosophy. And so we set ourselves the challenge of, wherever practical, all data will be in the public domain as soon as possible in accessible repositories. The thoughts behind this was that it would improve the scientific process, improve results, improve impact, and have more wow moments. And Cameron Nayland supported us through that process. So it requires a corpus of open and accessible resources. So we're looking at open methods, open data, open processes, open workflows, open licenses. And it should all end up with science in society. One of the nice things that happened as we were going through our project was that the Royal Science Society published Science as an Open Enterprise in 2012. We stated that open inquiry is at the heart of the scientific enterprise. Publication of scientific theories and of the experimental and observational data on which they are based permits others to identify errors, to support, reject, or refine theories, and to reuse data for further understanding and knowledge. Science's powerful capacity for self-correction comes from this openness to scrutiny and challenge. That statement is very powerful, and it helped us a lot in trying to explain this to colleagues and other people within the stakeholder community. At a very basic level, open science does not equal open access. Open access has been hitting a lot of headlines over the past couple of years, and essentially about making open publications, either in green, through an institutional repository, or gold by paying the journal itself to remove the firewall around it. Open science is really about opening up, is open access plus. It's about opening up the data, it's opening up your workflows, it's about embracing a scientific community and building different communities of practice to analyse your data, as well as publishing in an open way. And so open science is much more about the discussion and the process of data, whereas open access I see very much more about providing the lecture, providing the platform. So, open science. I see it very much dealing with engagement, data, collaboration, serendipity, impact, all within the realm of science. So from a data perspective, it's value-adding resources rather than creating static archives. It means that you've got a dynamic corpus that can change over time. It means that people can get access to your data who would normally not get access to it. So it has great teaching and learning potential. Also in respect of workflows, people can peer review your data, your processes at process time. And so you have lots of eyes looking at your assumptions and your approaches and saying, actually, that's right or that's wrong. It also allows us to look at trust and provenance and credibility. And so we can look at not just how good a researcher is because of their publication output, we can have a look at their impact as a data scientist. And I think that will become particularly important, and I'll talk about that more later on. And over time we should actually be able to have better models and produce better impact. We have open processes. At a basic level, that should increase understanding across the domain. Is transparency and reuse. You can see exactly how we've transformed our raw data into our interpreted data. You can reuse those processes if you find them fit for purpose. This is actually revealing the stuff which is only really alluded to in the publication model. And it empowers a whole range of different collaborations, both across disciplines. In DART, for example, we've looked at precision agriculture stuff, geosensors, producing soil maps, and we've collaborated very closely with Royal Agricultural University. But also within your own domain. We've managed to have some synergy now, obviously, between the geoarchaeologists, the ground prospection, the aerial prospection, and the aerial archaeologists, and all of this ties up to tell a much richer story. It should be able to improve impact. Your data can be used by more people. Your models can be used, again, by more people, but you're modelling based upon raw rather than generalised data. Because you've got access to more data, you should have a better decision-making process. And it's providing this whole reuse and engagement factor. You're engaging society. You're not blocking out segments. So it becomes a much richer experience. And so you can have impact in a broader spectrum and actually demonstrate it in a more coherent and solid way. And this is particularly important for open citizen science, as it allows many more people to become engaged within the archaeological process. And some of these are, we've been collaborating with the West Lothian Archaeology Group, where they do have rocket scientists working there. People whose understanding of physics is much better than mine or most of the people on the DART project. And so we can get specialists in and focus our attention on some of our problems and solve our bottlenecks, because we do need to now work in a much larger environment. We will not be specialists in all of the areas, and particularly the areas where we're having specific data bottleneck problems. So, why are we doing this? Well, the landscape has changed since we got funded in 2009. We now have the EU saying that we should do this. It's part of Horizon 2020. Enabling them, that is citizens interested in science, is not just good for science, it's also necessary for smarter decision making as the technical complexity of policy, from global warming to macroeconomic management, rises. Open science supports open government. UK government says so. This came from a Shakespeare review earlier on this year. Data, to optimise its value to society, must be open, shareable, and where practical, it should be free. Royal Society says so. Science is an open enterprise. I'll go through this again. And EPSRC says so. EPSRC funded research data is a public good, produced in the public interest, and should be made freely and openly available with as few restrictions as possible in a timely and responsible manner. It's a great statement. So, what did we do? We produced a data repository. This is based on CCAN from the Open Knowledge Foundation. It's a full metadata system. We used explicit liberal licenses, Creative Commons by attribution, and the Open Database license to encourage reuse and facilitate tracking. That's why it's by attribution. We use the OAI PMH metadata standard so that the data can be harvested from our environment and then discovered and reused through other portals, particularly the Archaeology Data Service and Europeana. The data has a URI, it means it can be called by web processors. We'll talk about this a little bit more later on. And CCAN itself has an API. So, here is our website. We can look at our data sets. Good. It's always nice to do this in a live way. vertical aerial photographs. This is a collection. In here we've got a little bit of metadata information about that data. We've got some keywords. Then we have a whole heap of other metadata about the instrument, bibliographic citation or data citation, link, a whole heap of Dublin Core related metadata information. All of this can be harvested by other people, and somewhere down here you will see the license for this data. Every single resource that we have is managed in this way. So we have metadata for basically thousands of data sets. They're all openly licensed, and it means that everyone can go in and see this stuff. I'll go and have a quick look at oh yeah, okay, and so you can go in and see here one of your oblique aerial photographs, location of where that image was taken, it's under a Creative Commons license, so on and so forth. And this is an ODBC BY because I see this as a data resource and not as an art resource. Okay, so we've got all of our data. This infrastructure does require core investment. Dart has sorted this one out itself. There are a number of data repositories available. It's part of a landscape that does need to change, and it does need significant investment. But it's not just about archiving, it's about providing dynamic and accessible repositories where information can change over time. Quick aside on licenses, we use Creative Commons by attribution and ODBL. Both expect attribution. That's how we can track impact. There are other clauses, share alike, non-commercial, no derivatives. Each of those clauses make the resource less free and have many unintended consequences for reuse and data migration. In addition, license management, where you're expected to manage it, is a cost overhead. Can you afford it? Examples of this are that Creative Commons share alike and Creative Commons non-commercial share alike are incompatible, i.e. you can't mix data up that have been shared, that have been provided under those licenses. And universities and museums are rarely non-commercial. A lot of people think that have a gut feeling that they shouldn't release their data to commercial exploitation. It actually has a whole heap of unintended consequences, so do get advice on these issues. We've also produced an integrated spatial temporal database. Here is the UML model for this database. Won't go into too much detail, but we can now put that through into Postgres, and we've provided that data through the repository, so anyone can easily install it if they have Postgres. This is ideal for online data mining. We've undertaken collaborative analysis. Most of this has been undertaken in Python, shared under liberal licenses to encourage reuse, and it's a basis of based on data with an accessible URI, so there shouldn't be barriers to implementation. So here's a quick example of one of our data analysis environments. Okay, so this is just telling which libraries you need to import. I'll run that quickly. This is telling you what data it's looking at. There's a citation, there's the URI from our portal at Leeds, and the data set, and it will open it out and it will print the data. So it's downloaded the data and printed it out as a list. Here, this is where we reshape the data prior to doing any analysis on it or printing on it, and here's how we can just plot that data. We could run a variety of other things on here, and what I will do is put this to show the multiple analyses thing. So because what I'm not going to do is to run this under Postgres. So let's get back to the deck. I could show you this under the database driven environment, but we really don't have the time. So what did we learn? Stakeholders really liked it. It generated an enormous amount of goodwill. It also enhanced collaborations and our network. People worked with us because we were giving things away. That was a novelty. We also have collaborations with Rachel Opitz and David Jordan from Mainz, who's looking particularly at reanalyzing and adding extra value to our data. So we got more data out of this because of collaborating with people. Data management is placed at the forefront of an exercise, so we're better organised. We can deposit our data with the ADS, which we will do anyway, in a much more streamlined way. We've built that cost in advance. Allows us to use web analysis frameworks. We can use distributed modelling. We also found out repositories are expensive and difficult to maintain and muster. We do need to resolve that through more institutional bases. Licensing and IP are complex. Open science is not seen as a universal good by academics. There are few incentives. Career trajectories are dominated by publication output, not by producing good data. The two should potentially go hand in hand, but we need to look at that. But this is something that's already understood by the Royal Society and others. People can see this as a loss of competitive advantage. Why give it away when you can squeeze the life out of it and get good things for your career? The perception is that it prejudices PhD novelty and publication viability. Depends on where you work. These views are complex and vary throughout the hierarchy and in different domains. From a heritage side, there are always issues about ethics. Who gets access to data? Now, the Portable Antiquities scheme uses accreditation systems, but I'm not necessarily. I think we need a more grown-up debate about this, and I'm much more interested in looking at ways of opening up the data and engaging local communities so we can have community stewardship in a more effective manner. What about the future? Well, we definitely need investment in infrastructure. Data and workflow repositories, interoperable catalogues, and this is not just a problem for academia. For Dart itself, we need to do some more data mining and visualization. We have a rich resource, and we need to start to pull out some more of those processes. We need to look at ways in which we can enhance knowledge-related practice and policy. Last year, we submitted, or a consortium has submitted a project called Thematic to FP7, which didn't get funded, but this was looking at developing new methods for monitoring, detecting and characterising heritage landscapes based upon multi-temporal remote sensing data and a better understanding of soil, so basically working Dart up into a larger project. Not just looking for detection, but also looking at risk and state, and how we can then feed that through into the whole decision-making process. We also want to look at creating a culture of open data and collaborative analysis, so looking at encouraging stakeholders to exploit the Dart and other resources, finding data deposition bottlenecks. We know that geophysics communities don't always deposit in a completely open way. Providing analysis cookbooks, just simple bits of code that allow people to analyse their data in interesting ways. Encouraging multi-stakeholder interaction, get some coders with some people with the problem, with some data providers, to find out how they can all work more effectively together. And we're putting this together through an AHRC follow-on fund. So, to wrap up, knowledge is a prerequisite to caring for England's historic environment. From knowledge flows understanding, and from understanding flows an appreciation of value, sound and timely decision-making, and informed and intelligent action. Knowledge enriches enjoyment and underpins the processes of change. Now, I think that's a great vision. I think that without open approaches, you'll have difficulty in achieving it. Thank you.